Hello, we are Team No Gas All Brakes. We are an electrical engineering senior design group, and this is our presentation for the fall 2025 semester.
Okay, now we're going to meet the team. Starting from left to right, I'm Justice Welch, software lead.
I am Gabriel Johnson, team lead.
I am Micah Carlton, the hardware lead.
I am Hunter Tucker, the research lead.
First, we're going to go over the design specifications for our project. The accumulator is going to act as our high voltage system that will be used to power the motor. The low voltage system consists of a 12-volt battery that will be used to power our other various electrical components such as the VCU, inverter, and BMS. The MRAX 228 motor is a small but powerful motor that receives 3-phase AC voltage from the inverter and will be used to propel the drivetrain. The Cascadia motor controller acts as our DC to AC inverter that will convert DC voltage to AC voltage. This is the device that the VCU will use to vary the motor's torque.
This is the potentiometer that we are using in the pedal position sensor. This is going to be what allows us to have variable speed within the system. This is the VCU 275. This is essentially going to act as the brains for our vehicle. It's going to receive and output data from the other devices via CAN bus. This is the PCAN USB adapter. We are able to use this to plug into the VCU to see everything that it's thinking via the CAN bus module. This is the isolation relays. It is a device that has both a high and low voltage, and that we will connect this through our shutdown circuit in order to preserve certain aspects of the vehicle should anything go wrong.
Moving on to our proposed system design. This is a block diagram showing the whole system and the way that it interconnects. As you can see in the middle, the VCU is communicating with everything, as well as our high and low voltage systems hooked up to the kill switch. So this is an image of our test bench. In the top left, you can see our MRAX motor. In the top right, you can see our 12-volt low voltage system. In the middle there, you can see that's the accumulators team model accumulator. It uses the orange wires there to power the high voltage system through the inverter. On top of the inverter in the bottom left, you can see the BMS. And then to the far right, you can see the AEM VCU 275, which is the VCU. So this is our acceleration position pedal sensor, reading out from 0 to 100% via AEMCal's software, hooked up to the VCU. And then this is our CAN bus lines incrementing RX and TX. And this is the readouts from our battery management system. We were actually able to configure the BMS to the VCU at the very end of the semester. As you can see, we got the different pack currents and voltages and the different high and low temperatures for the different packs also.
So this is the proposed design for our shutdown circuit. As you can see, the low voltage battery is powering the VCU, BMS, and other low voltage systems. In series with these devices are the shutdown buttons, which in our test bed we use a switch. When the switch is turned on, it allows current to flow and powers the isolation relays. This allows the high voltage side to also conduct and therefore allows power to go from the accumulator to the inverter. This video is showing us successfully showcasing the shutdown circuit. If you look at the voltmeter, you can see when I turn the switch on, it is reading approximately 105 volts. When I turn it off, it does not conduct. This is a still video of the shutdown circuit. The green wires are the high voltage lines. The one on the right is the negative terminal, and the one on the left is the positive terminal. As you can see, we have the isolation relays in series, and they are powered by the black 12-volt battery right there. And the two blue batteries on the right are test bench batteries. They are outputting approximately 98 volts.
We were unable to spin the motor variably with the pedal sensor. However, we were able to establish communication between the VCU and several other devices such as the BMS and inverter. Along with this, we were successfully able to implement a functioning shutdown circuit that future teams will be able to implement in the car's design. In final remarks, we want to say thank you to our sponsor, Dr. Ginga, for the opportunity to work on the vehicle, and good luck to future EEs who get to work on this project.